Yeah. Okay, let's see what we're doing now is the lab for linear regression over the regression chapter. Because as we saw, there's some theoretical stuff that we discussed when we are predicting a numerical value. But let's now see how we are going to do that using Python. Because when you're doing your data science, you're probably going to use Python, maybe R, but many people use Python now. So we're just going to import our packages. I'm not going to really get into the detail of every single line or highlight what is important. But since you have these notebooks, you can notebooks and the data sets, you can easily just go through everything I'm going through right now. So for linear regression and for linear regression, I'm thinking of logistic. It's coming in the next chapter. But for linear regression, let's see. We are importing our packages here. So we run that. We import our packages NumPy, Pandas, Matplotlib, and then we import some statistics because we are going to use some statistics. And then we import our VIF and ANOVA. You remember we discussed VIF, we discussed ANOVA when you're trying to compare models. So we are going to see that later. Then this one here is a very custom. It's a custom package. So this one you might not need a custom package, which is relevant for this course, not not relevant for others. It's relevant for this course. It might be useful when you're doing other projects or stuff, but in this course, it just makes it easier to run certain things. But you do not need it. I'm going to emphasize again, you do not need it. You can do your data science work just using the normal packages like these ones plus scikit-learn. This just has functions that are abstracted like load data. There are load data functions that are in there that just make it much easier to work with for us to explain us, but you do not need it for a project. So simple linear regression. As you remember, simple linear regression, we just get one variable and we try to predict what we're predicting. So here we're predicting median value. And in our original data set, we have 13 predictors, and the data set that we are using is the Boston data set. If you remember, the Boston dataset looks like this. This is the CSV itself. So in your data folder, you have the Boston dataset, boston.csv. It looks like this. But the problem is the it's not a problem. The thing that we're going to use, we're just going to use the function that is abstracted, which is inside our ISLP package, but that package is very specific to this course, so you do not need it. If you can just put Boston equal to pd.readcsv data boston.csv like that. The same thing. Here's just an abstraction, so we don't have to write pd.readcsv every single time in this course. But that's just it. But you can read it in this very same way using pandas. So here we're loading our Boston data set, or here we're loading our data set, and these are the columns. In that ISLP package, there's something called okay, we're going to see it later, but we're going to see how we do some feed transforms and all of that. We'll also use the stats models for the tasks of when we want to do some some analysis, statistical analysis. We're going to use that. So let's see, we've loaded our data set. Perfect. Now that we've loaded our data set, we can now use um, OLS. We can use ordinary least squares to fit an ordinary least squares model, which is our simple linear regression. And we're going to fit it on the median value using the predict. So we can do that. So this is just looking at the data set. So I can move it up here. We can move it up here because it's still just looking at Boston data set. Cool. Here we are now creating a spatial data set, data frame, where we just take the intercept. When you take the intercept and we are just creating ones, they're just going to be ones on the intercept plus the LStat. The LStat is going to be from the Boston LStat column. So we now have this data frame because we want to do simple linear regression. So we just need one variable. One variable that we need is the LStat variable. That's all we need. So that's what we are just creating here. And then after that, we just extract our y. What is our predictor that we want to do is the median value. That's it. We just created our y there. Let me actually put it on its own cell. That is our y value. Perfect. And then in this cell, we now fit our ordinary least square. Y being regressed on the X, which is our X data frame. This one here, that is the L stat. And then we just fit the model. So this part here does not really fit the model. This is the part that actually fits the model. So our results is equal to the model that we have created. Let's fit it. Then we fit it like that. If you want, you can just put dot fit at the end here, but here we just separated them into two lines. So this is now the resultant model that has been fit. Now that we have that resultant model that has been fit, we can look at summarize and then just look at the coefficient. Oh, so for the intercept, this is the coefficient, and for the L stat, this is the coefficient and the p values. That's what we do. Okay, let me just close this. Now let's remove that. We don't want to install anything right now. Cool. So that's the model that will fit here. But then sometimes you might want to fit transform. There's sometimes, if you remember well, about the effect of other variables on other variables. If a variable has a large range, it might overshadow the ones that have a small range. So sometimes you might want to force every variable or transform the variables to be between 0 and 1. You might want to fit transform, we might want to transform all of them to just be centered around 0. 0, or for them to move between, or for all the values in each of the columns to be between -1 and 1. You might want to scale, transform, and all of that. You can use some transformations like that. So yeah, that's what we're just doing. We are using the transformations. Again, not going through line by line because you can get this and then read what is going on here. So we are going to transform the L stat. And when we transform the L stat, yeah, it really doesn't do much. It's just one value. We're not really doing much transformation. But if you want, when you're using scikit-learn, so in scikit-learn, there is this package. It is a particular notion for this task, which is called a transform. A transform is an object that is created with some parameters and arguments. So you say, well, how you want to transform, and it has two main functions: fit and transform. Here we're just using the model spec, which is in part of ISLP package to do the fit transform, but you can use vanilla sklearn without having to use ISLP package. It is there. Fit transform is there. Import your sklearn. Your sklearn comes with the fit transform, just the same way that we're doing it. And you put your column that you want to fit transform and the fit transform that you want to use. Sometimes you might just want to use min max scalar. You want to use many different ones. They are part of sklearn. So you can do sklearn dot, I think it's pre-processing, and then after pre-processing you can choose. Let me actually test here. Import sklearn. Okay. Let's see. sk dot. I think it's pre-processing. Yeah, So we can do import from sklearn. No, no. I think it's you just import. Yeah, yeah. I'm doing this pre-processing. Okay. So let's say from import. I think it's min max scalar. So you see, min max scalar. There's multi-level binarizer, um, max upscaler. So there are many scales that you can get from pre-processing. So min max scalar it's a fit transforms, and then you can apply your min max scalar fit transform to your data set. So I will just delete this. But yeah, you can look at in scalar, which is your transformations. So here we're just using the one that we created abstracted, and then so yeah, we did it in two lines. We first fit and then we transformed. But if you want, you can just do the transformation, the fitting in one. And here you're fitting a transformation. You're not fitting a model. Okay, some people can loosely say we're fitting a transformation model. So you're fitting a transformation where it's a min max. So for your data set that is this big range, it's now being transformed into a range from 0 to 1. So you're now fitting and transforming your data set to be in a range of 0 to 1. After you've done that, this one we really didn't do it here, but in models later we're going to do it. So when you fit your model, This is just a transformation. This is the part of just transformation. But the model that we fit here, I should actually maybe move this around. Remember the model that we fit up there. What you can do is actually, okay, let me see if I can just move things around. Let me take this cell so that it flows, so that the learning will flow without having to be disjointed. Okay. Okay. Right. Let's see. Yeah, let's put the transformations there. So you remember the model that we fit here. We fit a model on our data set X, on our data set X, where we regressed Y on that X, which the X just having the L stat. Remember well. So cool. These are we summarize. We use summarize, but summarize just gives you a taste of what is going on or a taste of the results. I am using the summary because the summary is just a function that is created in the ISLP. It is not something that you normally use. What you normally use is after you fit your model, dot summary. Dot summary. This summarize just takes a bit of the summary and then it's a custom function. So don't worry about that one. But when you fit your model, do dot summary. What do you get back? Depending variable that we're doing is we're predicting median value. The model that we used, OLS, the method of fitting was least squares. When we did it, number of observations, residuals, and all of that kind of stuff. R squared, 0.54. Not really a good model. Adjusted R squared, if you remember, adjusted R squared allows you to compare different models with different number of predictors. But here we just have one predictor, so it's fine. They are sort of like similar, so it's okay because simple linear regression just uses one variable. Statistic, then the p-value of the F statistic, cool, which means L stat is actually very is an interesting variable, as you can see here. But let's AIC and then BIC. As you can see, this is part of the summarize that we just had. But yeah, so the coefficient. This is the coefficient of the intercept, coefficient of L stat, the standard errors, and all of those skewness. This is the p-values and that. Cool. That's the result. You can get the parameters. Just extract them by using params. So now you have a parameter for this is the beta note for your intercept, and this is the beta one for your L stat, which is the variable that we're using in this case. Cool. So now that we've seen how to do simple linear regression, what we want to do now, let me see. Mm, and then we are using fit transform. Supposed to discuss the fit transform. Let us now see. So now that we have done our fit transform here, we now have a new value that we want to predict. We have a results model. The object results has several methods in it. We can use summarize and all of that. Let me actually arrange these. Now my are not well arranged, but the notebook that you get will be very well arranged with a story that flows so that you do not get confused with like fit transforms and all of that kind of stuff. Um, so maybe I'm just wasting time actually going through the rearranging here. I'd rather leave it here and then I rearrange and I'll send it to you when it's better arranged with a story that does make sense. So now we've done our fit transform, we have new, we have new, we have new, we have new predictions that we want to make. We now, let's say we have L start with these values 5, 10, 15. We now want to predict what is their median value when the L start is 5, when the L start is 10, when the L start is 15. What is the new value? So we create a new data frame with that L stat, and then we transform it like we did previously. So here, we fit transformed design. We created design, fit transformed design. We're just going to apply that design that we fit transformed here. That's the thing with machine learning. When you have fit a scalar from whatever range is the variables here to 0 to 1, When you have new variables now or new values that you want to use to predict, that's new. We haven't seen them before. You just apply the transformation. You don't fit transform anymore. You just apply the transformation because you want to fit transform that was done during training of the model. You apply the same transformation to new to new data. You apply the new transformation to new data and you create a new data frame. So this is the new data frame with the transformation that we did during training phase. And then, so this is the one we're going to use that as the new data frame. And our model, the results model, we are just going to say dot get prediction. It is a function that it comes with our simple linear regression model. So it's just say get prediction for our new data frame. We do not know what the median value is supposed to be. So tell us what the median value is supposed to be. That's what we're doing here. And we get these new values. So when L stat is 5, this is the median value. When L stat is 10, this is the median value. When L stat is 15, this is the median value. We can also produce confidence intervals. So this is alpha of 0.05, 95% confidence interval. This just means 95% confidence interval. So let me just type that 95% confidence interval. So 95% confidence intervals. So for the first one, these are the 95% confidence interval. Second one, third one. We can also put OBS equal to true to get our prediction intervals. So this is also 95% prediction intervals. And as we said in the theoretical section, prediction intervals are always wider than the confidence intervals. As you can see, this is 17 to 42. Confidence interval is 29 to 30. So for our value of 10, if we have an L stat of 10, we want to predict, we have an L stat of 10, let's get our L stat of 10. We fit transform it, right? We fit transform, or no, we don't fit transform, we just transform it because we're predicting now. Transform it. This is our L stat of 10. We now apply our get prediction. So our get prediction applies it and then says, oh, the prediction that I'm going to do is 25. So for that L stat of 10, the median value is 25. And this is the confidence interval, and this is the prediction interval. As you can read here. So the ISLP package, as mentioned before, it is a custom package, but you're not going to have it in your projects. So here we are just creating a function by ourselves. So inside the ISLP package, there are functions like these that are then abstracted, where we don't have to really, like our load data, we don't have to write pd dot read CSV. It's just a function, but the function will just be defined load data, and then it will say Boston. So actually, if I can show you, def load data, it would then just say dataset. What is the dataset that you want to read? Return dot read CSV, and then it will say something like location or whatever, OS location or whatever. But at the end, it will just say the dataset. It will be dataset. This is pseudo code. It's not going to be the right code itself. Dot CSV. .csv. So here to say something like data data plus dataset. So which means now when you call that function load data, and you give it Boston, and you give it Boston like this, it will then put Boston here, and then it will say pd dot read CSV Boston dataset. So what gets returned here is the pd dot read. It returns the data frame that has been, but this is just the abstraction that is inside ISLP, so that you just load without pd whatever it is. But that's just it. But sometimes you want to write your own function. So here we're writing our own function. So our own function that we're writing is AB line, and that function just draws a line. It simply draws a straight line. So it draws a line, it gets the x limit. So what is the x limit? The x limit is going to be what is the x0 and what is the x1. The limits of x in our plot. And then here it just gets y1. If you remember, y is equal to mx plus b. So this is just y1, which is y0 actually. Y0, which is y, plus the x limit, the first x limit plus b. And this is y1. The second x limit, which is just the topmost x limit of limit of x. So this is mx plus b. So here we're just going to plot a line from which is going to be x0. So here what is actually doing a line from x0. Yeah, it's plotting a line from x0, x1 to all the way to using other coordinates y0, y1. That's what it's just doing. X0 to y1, and this is the y's. That's it, pretty much. So that's our function there. You can read about this function as well. But why are we doing that? We are doing that because we want to look at our data. If you look at our Boston data, these are the dots, which are our these are the values actually, the actual values in our data. And this is the fitted line that we had. So the results, parameter 0, 1, parameter 0, params 0, and then params 1. If you remember our parameters that we had, we are using our up line now, the function to draw a line. So this is the result of our model. So this is the result model that has been fit. Is that a good line? I don't think that's a good model because as you can see, there's some shape here in our data. It looks like curved like this. But as we fit a simple linear regression, a simple straight line, it doesn't look like it's really capturing the data, the information in the data. And it makes sense because if we scroll up, I think when we looked at our results, they were not satisfactory. Remember, our scale was just 0.54. That's not a good performing model, right? It's not a good performing model. So this doesn't look nice. This doesn't look nice. There is some non-linearity here, but we are forcing a straight line as the model, which is a problem. So let's go. Let's scroll down. Let's plot our residuals. If you remember, well, we can plot residuals as a way to actually see if there's non-linearity. Because if the residuals have some shape in them or some pattern in them, non-linearity. And as you can see, there is a bit of a shape here. It looks like it's curving like this. There's a bit of a pattern, a bit of a pattern, which means if our residuals have a pattern, there might be non-linearity here. So fitted value plotted with the residual show that there's might be non-linearity. So what are we going to do? We are going to do multiple linear regression because our straight line does not prove anything. It does not work. So what are we going to do? Multiple linear regression. Again, we are using model spec, but you can use scikit-learn without using model spec here, without using ISLP. So when we fit our multiple linear regression, is just going to use two variables for now, Elstat and age. We fit transform them, we put them in our model, and then we fit our multiple linear regression model. Cool. We summarize. If we want, here we just said summarize, but if we want, we can use summary like we did previously. Dot summary without using the custom summarize function. Our summary just says the same thing. This is the variable that we're doing. We are fitting with all least squares. We have now 0.55. Instead of 0.54, we now have 0.55. Slight improvement in the model. And these are the coefficients. Coefficients of the Elstat. So this is beta naught, beta 1, beta 2, Elstat, and then age, and all of that kind of stuff. Cool. Now we actually have more, so you can play around and see how all these other columns actually change the model. We just dropped the median value because that's our predicted model, right? That's the predicted value that we want. Here we just fit with all the models, that all the variables. We fit the model with all the variables, summarize the results. If you want, you can, instead of using summarize, again, results.summary. So now, if we don't want to use the age, we can fit another model without the age with the median value, of course, because that's the one that we are predicting. So we don't need to, it will be our y, it will be our y, and then our x will be the x without the age. Cool. But we're just playing around. It's a science. Data science is a science. We play around. We play around to see what actually makes sense. Here we look at our goodness of fit. We remember we looked at our VIF. So we encounter a sequence where we would like to fit transform. Below we compute our VIF for each feature. matrix and produce a data frame whose index agrees with the columns of X. So these are the VIF values, but when you look at them, they're not very informative. Yeah, these VIF values. So what we can do is let's look at interaction terms, because maybe our model, even though we might look at it with just Elstat and age, but maybe there could be interaction between Elstat and age. Again, that's where the science comes in of the data science. You play around. So here we're playing around. We're not fitting a model that is Elstat, it has age, and it will have an interaction between Elstat and age. That's model number two. Fitting that is model number two. So it has Elstat by itself, age by itself, and an interaction of Elstat and age. This is the beta 3, which is the interaction of Elstat and age. And then we can see, does that, let's actually see here, model 2, model 2 dot summary. Well, let's look at what the result is for model 2 dot summary. Did I feed it correctly? Um, why am I not getting summary here? Oh man. Well, we haven't fit the model actually. So, I no, I think we fit the model, yeah. So that's weird that it's not giving me a summary the way I want it. Yeah, it's supposed to be like summary like that. That is extremely weird. That is telling me that model, and I cannot figure it out now on the core on the video, lest it becomes too long. Actually wonder what's going. Okay, yeah. Hopefully I'll figure this out before I send the notebook, and you can see the proper summary. Um, and then, but this is just for them. We want nonlinear transformation of the predictors themselves. So here we want to put a polynomial prediction, a polynomial predictor using Elstat. So we have Elstat to a degree of 1, but we might have Elstat squared. So here let's put a model that is Elstat squared. So this model we have Elstat squared. Cool. So this is the coefficient for intercept beta naught, beta 1 for degree 0. And then here this is when it's now Elstat squared, this is beta 2. And then we have our beta 3. Now that we've included a polynomial, let's try look at ANOVA. So ANOVA, we are now saying with our ANOVA, we want to compare. Remember, our results one was just the one where's our results one model? It is the one that just had Elstat. It was just fitting Elstat, and it was the one that was fitting this one here. It was fitting a model that just uses Elstat and age. That's it. Elstat and age as the two variables. But here now we fit in Elstat. We fit in Elstat. Where is it? 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 Yeah, here we're fitting Elstat. We're fitting age, and we've also fitting Elstat squared. So we want to see what is the performance, what is the difference between those two models. Again, you're gonna just look at their R squared, and then you'll be like, yeah, R squared are different, is better for this model than this one, yeah, because they're different predictors now. The first one, results one, is just Elstat and age. The second one here is Elstat, age, and Elstat squared. So they are different predictors in different formats. So we cannot just use R squared like that. We can use ANOVA. ANOVA compares the two using some statistics and hypothesis testing. The H naught for for the hypothesis testing, or the null hypothesis for ANOVA, is that the quadratic term is not needed. And then the H1 is saying we need the H1. H1 says we need that polynomial term, or in other words, the model that is the polynomial term is a better model, is a superior model. That's what is just saying ANOVA here. And as you can see, when we run our ANOVA test, you can see that the F statistic associated F statistic and the associated p-value is large. So the F statistic is very large, 177, and the associated p-value is extremely small, which means it is way less than zero. What that then means is we can now conclude that we can reject the H naught because the p-value here and the H and the F status are showing that this three, that is the polynomial term, is actually significant, is statistically significant or statistically different to this result one that does not have it. Because we're just comparing, is the result three statistically different to the result one? It is statistically different. So one is statistically different. So now we can say, okay, the R squared that is coming up here, it is interesting. It's actually interesting here. So in this case, the F statistic is it is a square of the T squared. So function ANOVA, it takes these two models and then makes a conclusion. So now, if we want, we can look at our residuals again. Let's look at our residuals now with that results three. Results three model again. It is the L stat, the age, and the L stat squared residuals. See, when we plot the residuals, there is no discernible pattern here. It looks like a rectangle or it looks like something. There's no discernible pattern that we can say there's an actual pattern compared to before. Before we could tell there could be a curve there in the residuals, but here there's no discernible pattern. There's still a bit of it, which means we can, instead of L squared, we can do a polynomial with L cubed. We can test that. We can test that. Then that's where the experiments come in data science. We can cube it. You see here, we can cube it or even put it to higher polynomial fits. Or do that for age. Do that for other variables. Do that for, and then that's where your experiments come in, and you track your experiment. You're like a physicist or a chemist in a lab, and then you do your experiments. You're like, this is the result, and then you chase that result that gives you better value, and all of that. That's all you're doing here. So that's what we're doing. Homework will now be: can you use the car seats dataset classes data set and do what we've done here and follow the tutorial here. Do what we've done, fit your model, and see how that comes up. But this is the lab for regression. We're going to do the lab for classification as the next topic. We'll do the theory and then we'll do the classification lab. So stay tuned for that video.